Hello, everyone. Good morning, good afternoon, and good evening. Welcome to another Fusion 360 live stream. I am your host for today, Jason Lichtman, and I am accompanied by Brad Tallis on the keyboard. So if you have any questions throughout today's live stream, feel free to ask. You are in good hands. Today's topic rather, is going to be tips and tricks for 3D printing. And to be clear, this is not going to be about the settings you use in terms of like the temperature or like the raft size or your layer height or any of those kinds of things. We're going to be focusing more on the design for 3D printing. This is often called design for manufacturing or DFM. And DFM is all about designing for the manufacturing process you're going to be using. In this particular case, we're going to be talking about designing for 3D printing and some tips and tricks that I've found that are going to be helpful in getting good prints and getting those prints quickly and easily. As you could tell, I have a 3D printer behind me right over there. It is a MakerBot Method X Carbon. I'm often asked what that is, so I'll make sure to tell you. I'll tell you a little bit about it. It is an FDM or FFF 3D printer. FDM stands for Fused Deposition Modeling, but it is a proprietary name, so a lot of companies prefer to use FFF, which stands for Fuse Filament. What's the last F? Fuse Filament. I don't know. It'll come back to me in a second. But we're talking about a 3D printer that uses a spool or a reel of filament, which is the plastic that you're going to end up using for your 3D printer. This particular one is extra special because it can print in nylon with carbon fiber, and it also has a heated build chamber as opposed to a heated bed. And that allows me to print in nylon with carbon fiber very well without any distortions, without any warping or anything like that. This printer is awesome. I'll probably tell you a little bit more about it later, but really we're going to focus today on the design for the 3D printing. Whether you have a printer like this one, or you have a lower cost printer, whether we're talking about a Flash Forge or a Creality, which are getting very, very popular these days, we're going to try to give you some of my favorite tips and tricks to be able to get those prints easily and quickly. So let's actually show you the list because I think that's going to be helpful. So here you should be able to see the list of the 10 tips and tricks I'm going to show you today. I'll just briefly describe them and then I'll actually show them. The first is about using parameters from the parameter table inside Fusion 360. The next one is about minimizing Z height of your part so that you can get your parts faster. The third is about fillets. I love and I also hate them, especially for 3D printing in particular. The fourth is about testing your feature instead of your entire part. That'll make more sense when I go through it. The fifth is about accessibility analysis and draft analysis to make sure that you can minimize those overhangs and your requirements for support material. Then we're going to talk about the FFF consultant, which is like the accessibility analysis or the draft analysis, but it's fantastic specifically for FFF or FDM printing. I'm also going to talk a little bit about using Generative Design's additive manufacturing constraint so that it actually automatically designs 3D printable structures for you. And that's a huge time saver. We're going to talk a little bit about the Zometry app that is free for Fusion 360 and how it lets you cost out 3D printing your parts or CNC machining them and a whole variety of other manufacturing processes as well. And even if you do have your own 3D printer, that will prove useful. And then we're going to talk about two mesh workflows. One of them is how to convert a mesh into an editable solid. And then the second one is going to be about how to take a mesh that's really heavy and add engineering features to it using solid modeling without having to convert it into a solid. So that's the list of 10 things. I think that that's going to be a fantastic use of our time today. And so with that, I think we should probably kick things off by jumping right into Fusion 360 itself. So let me go and grab the right screen here. Hold on just a moment. I'll share my screen. We are starting off with a blank file. I call this a starting file because this isn't just the blank file that you get when you hit the plus sign up here on the new design area. This is a starting file that I already created, and it's really simple with what it has in it. If I go to the modify dropdown here and I go to the very bottom, you'll see change parameters. And I actually added a keyboard shortcut to it because I use this quite regularly. And let's go and pull up that parameters list. And I already included 4 of my most favorite parameters. They're going to be nominal wall thickness, and that's going to be like the wall thickness I use most often. The minimum wall thickness, how low can you go or how thin do you want to be able to go? I have another one for nominal radius. That's, the most common radius size I'm going to end up using on my particular part. I do like consistency, so I typically use the same fillet size wherever I can. And then in certain cases, I want to fillet, but I want it to be as small as possible. So I also have a parameter here for minimum radius. Now you can create these on the fly whenever you'd like. So if you want to end up making a new one, you can go and create that. And we're going to call this maybe height of my part, and we'll go and set that to 20 millimeters for now. But you get the idea. You can go and create parameters very easily. And if you start off with a starting file like I've already done, you don't actually have to do that because it's already done for you every time. But the benefit of this parameter table is that as you're designing something, you can use those numbers really quickly and really easily. So if I'm designing an electronics enclosure, and I'll make this one very simple here. We'll go and just draw a quick rectangle, starting in the center. We'll set this to, let's see, we're going to go with 100 millimeters wide and maybe 50 in this direction. And I want an offset for the walls. So we'll go and make an offset. And this is where the parameter starts to become helpful because I can start to type in wall thickness and I'll see that parameter list of whichever one has the words wall in it show up. So do I want this to be really thin? Do I want it to be my minimum wall thickness? Probably not. I want it to be my nominal, and I'll go and hit OK. And now I have my sketch with everything how I like it. Then when I go to extrude my model, and I like to rotate it a little bit so I could see this a little bit more clearly, I'll go and select the center as well as the wall here, and I'm going to extrude this up. And how much am I going to extrude that? Again, that wall thickness, and I'll choose that nominal wall thickness just like that. Lastly, when I end up wanting to make the walls themselves, I'll go and select the profile of the wall. And in this case, we're going to start it at an object, which will be this top surface here, and then I'll drag this wherever I need. But the idea behind the parameters is that I can very quickly and easily reference a set of numbers that I use on a regular basis, just like you saw here. And if I do want to change anything in this parameter list, it'll go and change this globally in my part. So if I change that nominal wall thickness to, let's say, 3 millimeters, my entire part got thicker. Not just the wall around the perimeter, but also the cross section of the underside. And you'll see that if I go and I make a section analysis for you, like so. That bottom wall here is also driven by that parameter. When I am ready to go and put things on like fillets, I can go and of course do that. And I'll go and hit the F key for my fillet tool. Maybe I'll go and select this, let's say, outside edge, and I'll go and put it on all 4 corners, rotate around a little bit and grab this one as well. And again, I could just go and type in, this time nominal, and maybe I'll pick that nominal radius. Or if I really want this to be tiny, I'll go and just type in radius, and I could pick that minimum radius, and it's just there ready at my fingertip. So this isn't going to affect your part quality per se, but this is very much going to affect how quickly you end up getting to your final part. I think that this is a very helpful tip. And if you've been using Fusion 360 for a long time now, you've probably already known this. But for those of you that are newer to the table, I think that you'll like this. Second item on our tips and tricks is about minimizing the Z height. And the Z height is not always about, the actual Z in my file. Because if you look at my file here in the top right corner, I could see that Z is actually left to right. But when I say Z height, we're really talking about the overall height of the part itself. And the reason that we're talking about the height of the part instead of the width of the part, which is what you're seeing on the screen at the moment, is because when we're talking about manufacturing, in this case 3D printing, The Z axis is typically up and down relative to the extruder of the machine. So if we're looking behind me at my MakerBot Method X, actually let's go and zoom in a little bit here. The up and down is definitely the Z height that we're talking about. Perfect. And in my coordinate system inside Fusion 360, Z is actually the default for up and down, but I use Y up because I come from a SolidWorks background and SolidWorks tends to use Y up. But the point is simply, regardless of what the coordinate system says on the top right corner, the Z is really the height of the part. And why does that matter? Well, as the 3D printer is going to go and 3D print your part, it's going to go around in X and Y. And then once it's done with a layer, it's then going to go up, or the tray or the build plate is going to go down so that it can then do the next layer. The height, the Z, tends to be the slowest thing within 3D printing. So if you can minimize Z height of your part, you're going to get your final part much, much faster. And that's not to say that you should change your design completely so that it's just a lower height part all the time. But it is to say that when you're ready to 3D print something and you want to test something, and we'll talk about the testing aspect in just a little bit, the Z height is the most critical when it comes to the timing. So if you can take your part and orient it so that the Z height is lower, you're going to get that part faster. But the trade-off might be that you need more support. And I'm lucky, a part like this, or sorry, the printer behind me has the ability to print in SR30, which is a semi-water soluble support material. I have a special heated bath chamber on the other side of this wall, and I put my parts in and it removes that support material. When the part actually comes out of the machine, it looks something like this. And the white layer, that might be a little hard to see. Let's see if I could zoom in a little bit for you. The white layer here, that's the support material, and this is dissolved away in that bath. But if you don't have a machine like this, and you're printing just using the build material as your supports, just know that those supports are going to leave artifacts or imperfections in your part that you're going to have to clean up. And even after you clean up, you're still likely to see for the rest of the life of the part. So there's a trade-off between the Z height and those artifacts from support material, but just know that in general, whenever you can reduce that Z height, you are going to get a better experience overall, and it's going to be faster in particular. So minimizing Z height can be pretty important. The next thing is about avoiding fillets. Now, fillets are a blessing and a curse. So fillets can do a number of good things to your part. The first, actually, we don't need the screen for this. So let's go, this is better. So the first is that it makes your part look nicer. It gives it more of a softer edge or a softer shape. It also can make it so that your part isn't going to be sharp to the touch. That I think is really important as well. And the third important thing that fillets do is that it reduces stress propagations when you're talking about loading your part. So if you have a part like this one and you go to start bending it, any sharp corners are where it's likely to break. So fillets are really good at making your part stronger. But fillets are also really good at causing headaches when it comes to 3D printing. So your 3D printer, especially an FFF or FDM printer, has a layer height, typically around 0.1, 0.15, 0.18, 0.2 millimeters, something like that. And when you end up with a fillet on your part, those layers are going to facet that fillet, and it's not going to look as good as you might want it to look, typically. And I'm sure in the comment section now, people are going to write that they print with fillets all day, every day, and they have great luck. But I'll tell you, for just as many of them that have great luck, you're going to have people that have very bad luck with fillets, and they can solve that with futzing with their extrusion temperatures and a bunch of other settings. But if you don't want to futz with your settings, just know that fillets can cause headaches with respect to your part quality. And that's especially true when we start talking about fillets on the underside of your part, right against that build plate in particular, at least from my experience. So let's go and show you what we're talking about. I'm going to share my screen again. You'll see this very basic design that we just started here has no fillets along this bottom edge. And typically, I like to keep it that way whenever possible. This will yield a much better part than if I added fillets at the bottom. The same is also true on the top, but less so. The bottom against the build plate tends to have a big effect, is what I've found. So when I'm printing parts, like let's say this insulin vial rack that's coming up here, if I'm printing this yellow part with these blue surfaces against the build plate, those fillets at the very bottom tend to be the most problematic. I might do it anyway because that's what I really want in the final part, or I might even print it without the fillets, and I might even sand it by hand. Not a big deal to sand by hand every once in a while. Got to use these hands sometimes. The alternative is printing with different technologies. So SLA 3D printers, SLS 3D printers, Hewlett-Packard Multi-Jet Fusion 3D printers all have different limitations. So when we start talking about design for manufacturing, we're not just talking about design for 3D printing in general, we're talking about designing for a specific method of 3D printing. And I'll tell you that even within FDM or FFF printers, there's still variation. So if you're using a printer that does not print with water-soluble support material, like SR30 or some other options out there, the removal of those lower fillets tends to be more important. But because this particular machine prints with the heated chamber and prints with the SR30, I actually add fillets wherever I want, pretty much any time, and I have great results. But if you do not have a printer like that, one of the things you can try is removing those fillets. Again, especially on the underside of your part. Next part, or rather next tip and trick is about testing your feature instead of testing your part. So let me show you a different example of that. In the machine right now, and let's go grab that part. Go and see here. There we go. Perfect. All right, so in the machine, I have this part. And this part is a holder for a bear spray canister. I live in Colorado. We have bears. It's a real thing. I live right against the foothills. We have bears right by our house. And so I keep this bear spray can at various areas around my house, outside of the house. So if I'm outside and a bear shows up, I have this handy. And in order to store this, I have printed a bunch of these things. And these are fantastic. They fit perfectly and I think look pretty good and relatively discreet, besides the blaring orange sticking out. And when I'm trying to print something like this, and I want to see, is this part going to fit together well, or is it going to jiggle too much? Is it going to be too tight of a fit? This is the kind of thing that I might want to 3D print just to test. So when I'm 3D printing it to test, could I print the entire bear spray holder? Yes, but remember that Z height tends to be the slowest thing. And I'd be using a lot of material only to find out that potentially my part doesn't fit or is too loose inside there. So what I recommend is to be able to test your part in sections. Test the feature, so to speak. So right now we're looking at my screen and you could see my 3D model of my holder as well as a very simplified representation of the bear spray itself. And if I want to test this, I'm not testing it by 3D printing the entire part. Instead, what I would do is I would create a quick offset plane on maybe this top surface here. I'm going to lower it by maybe 10 millimeters, I think would be fine. And then I could go and do a split body of this particular body using this particular plane. I now have two bodies. I have the top as well as the bottom. And I could go and just remove the bottom and focus on the top. This is what I would actually 3D print. And I could 3D print it by itself, and it's going to print very quickly because the Z height is only 10 millimeters, not 80 or 100 millimeters. And again, Z height is going to be the most important with respect to. Just a moment while I cough off screen. All right, I'm back. So by printing this as 10 millimeters tall, I'm able to get that result quickly. And if I want to get the result even quicker, I might make 3 variations of this particular ring with different inner diameters. Maybe it's a 1 millimeter gap, maybe it's a 0.5 millimeter gap, maybe it's a 1.5 millimeter gap. And so I print all 3 of these at 10 millimeters tall or maybe 5 millimeters tall. And then I get to figure out what is the best fit very quickly, apply that to my final part, and then I'm going to go and print one final full version to test the final result. And keep in mind that you could do that for all sorts of things. So for a part like this, I might actually print just the top section to figure out the diameter that I want. And I also might print something like this area, which looks a little bit funny, but this is meant to be able to get a screwdriver to fit in here and a screw to fit in so that I could actually mount this to a wall. And I might want to be able to print just a section of this ring to be able to verify that everything is actually going to fit and I could reach and the screwdriver's long enough and so on. And I can do all of that in sections instead of printing the entire part, because again, printing that entire part could be a 4-hour print instead of a 30-minute print. So I think that's pretty useful. Let's go back to our PowerPoint again. So test your feature, not your part, and print variations or a single feature or parameter. The next one is going to be accessibility analysis and draft analysis. So let's go and take a look at another example. Go back to Fusion 360 here, and actually we want to open another instance of Fusion 360. Here I have it, and this is the one we want to look at. All right, so this is a Yeti mic stand. And a Yeti mic is a fancy microphone. It's the microphone that I'm using right now, and it is actually sitting on a 3D printed microphone stand. It looks very similar to this with a slight tweak to it because I printed this one, tested it, and then of course wanted to make a tweak. That's pretty standard. And then I printed a second one. That's what the mic is on right now. But what I want to show you is how you can analyze your part very quickly to see if it's going to 3D print well on your printer. So let's go and take a look at those two tools we're talking about. They're both under Inspect. The first one is called Accessibility Analysis, and the second is going to be called Draft Analysis. And accessibility analysis is all about checking whether you can access various different parts of your component from a particular direction. It's especially useful for CNC machining to verify you don't have any undercuts, and it can also be used for 3D printing to verify the same. So I'm going to choose the accessibility analysis tool. I'm going to pick my body, and then once I pick the body, I'm going to choose the direction that I'm going to analyze it to. So this is typically, think of it as the bed of your 3D printer. And for a part like this, I already know that this is going to sit flat against the bed of my machine. So I'll go and select that, and it's going to colorize my part. And there are a couple of options here to play with. Direction 1, Direction 2, and both directions. Direction 1 and 2 are going to be the difference on what's red and what's green. And if you choose Direction 2, it's essentially going to look at it from like a different direction. But keep in mind that it's actually using not just the direction itself, it's actually using the surface that you picked. So you'll notice that it's not just flipping the colors, you get a slightly different result depending on which of these you pick. But really it's all about seeing, can you reach it from that direction? And you'll notice here, the only area that shows up as red within the green is this area over here. And that area is an undercut. And it's an overhang, so to speak. So I cannot reach this bottom area directly from below because there's material underneath it. These are going to be areas that you might end up having 3D printing problems. But keep in mind that FDM or FFF printers are fantastic at doing overhangs under certain conditions. So there's an overhang angle, typically 45 degrees. You can play with that though. You might have better luck with 40 degrees. Or, for metal 3D printing, it tends to be a lot lower, more like 30 degrees. But the point is simply, there are overhangs that are acceptable. This is really just identifying where those overhangs exist in the first place. So if you see red within green, or you see green within red, that is your overhang, and you might want to take a look at that in a little bit more detail. And again, play with these options to really understand what they're doing, but they are identifying those overhangs for you. The next thing you can do, oh, and by the way, these analysis tools will stay for however long you want. So you can actually continue to design while seeing the green and the red. So I can continue to create new geometry, and as I'm designing it, I'll see in real time whether I'm creating overhangs that would be problematic. So just keep that in mind as well. You can always turn off the little eyeball and then that goes away. The other tool I like is the draft analysis. And I'll admit, I use the draft analysis for a lot more than 3D printed parts. I use it a lot for molded parts. I have a specialty in injection molding and foam molding and also composite material molding like carbon fiber parts. And so we do a lot of draft analysis for those kinds of applications. You can also use the same for 3D printing. It works very similar. You're going to choose the body, you're going to choose the direction. In this case, again, I'll choose the bottom of my part. And then it's going to colorize your part in 3 different colors. You're going to see blue, you're going to see red, and you're going to see green. The red sections are the areas that do not have enough draft. And the blue sections and the green section are going to be the ones that have enough draft in a particular direction. So blue is one side and the green is the other side. And this is not a perfect tool for the overhangs that we're talking about, but it is still useful. And the reason it's not perfect is because you'll notice that the draft angle limits go up to 15 degrees. And what I would really like to see here is 45 degrees. Because what that would allow me to do is to just check very quickly whether this is within that 45-degree limit that we're talking about. But just because it doesn't let you do that doesn't mean that this still isn't useful. Because again, what you're seeing here when you start messing with this is the same areas that you were seeing with the accessibility analysis. The green area is essentially an overhang, and so it is identifying that for you so that you can go and look at it further. If you would like a better tool than this, there is one made by Autodesk. So I'll show you what that is. And I'll just show you the list here. Again, remember, is the FFF consultant. So let's go back to Fusion 360. We'll exit out of this analysis here real quick. And we're going to bring up that FFF consultant. You're going to see it right here, and it's called Additive Assistant, or FFF. And this is not in your Fusion 360 by default. So to be clear, you are going to have to add that. It is a free add-in, and you can find it on the App Store. You go to Tools, Add-ins, you go to the App Store. It'll open up a web browser. I'm using Google Chrome, and here it is. And then you can search here for Assistant and hit Enter, of course. And here you have the Additive Assistant. This is available today only on Windows, so I apologize for any of you Mac users out there. But for the PC users, I think you will love this app. And again, made by Autodesk. So once it's installed, you're going to go back into Fusion 360 and you're going to run it. So you go to Add-ins, Scripts and Add-ins, go to Add-ins itself, find the Additive Assistant and hit the Run button. If you want to use it automatically every time you open Fusion, also check this Run on Startup button. Once you've done that, you're going to find it again, like I showed you at the beginning, right here next to Inspect. And you're going to choose the Additive Assistant. You're going to choose your part, choose your material that you want to 3D print in. And many of you are using PLA, even though I use nylon primarily. But we'll choose PLA, and you could choose your build volume. And my printer is more like 150 by 150 by 150. And I'll go and hit the Inspect button. Now, I'll tell you right now that I'm going to get an error, or not really an error. I'm not going to get results that I was liking, because what this is doing is instead of it asking you where the build plate is going to be, it assumes, and we all know what happens when you assume, it assumes that the Z direction is the build plate direction. And in this particular case, I'm building with Y up, and so it's putting that build plate over here on the side, which is incorrect. So I'm not getting good results. But that's a really easy fix, right? You can either use Z up as your options in Fusion 360, and many of you already have that. That's actually the default in Fusion. I'm one of the outliers who's changed it to Y up. But you can put it back to Z up, and then when you design a new part, it'll already be in the right orientation. If you're like me, though, and you prefer Y up because you're just a maverick like that, that's okay. What you could always do is just add a feature into your timeline where you select your body, you're going to do a rotate, in this case, using the x-axis, and we'll rotate this 90 degrees. And as I'm designing, I would probably suppress that feature so that I design using Y up. But when I want to use this additive assistant, I would just unsuppress that feature, and now I can actually go and use the tool. So let's go and rerun this, and I think we'll see the results as I was hoping they would look. Takes about 10, 15 seconds for most parts. More complicated parts might take a little bit longer. Let's rotate this around so we can see this a little bit more clearly. Good. So now we see the part is actually on the build volume. So that's what I wanted. And what it's going to do at this point is it's analyzing your part for a bunch of things. The overhang that we were analyzing before is one of those things. So you can see overhang check is looking good. And if I want a little bit more detail, I can hit this little I for information, and it's going to tell you what the overhang is and where it is on this particular part. It's a little bit hard to see at the moment, but it's actually highlighting in red that same overhang that we were looking at just a little while ago. So you could then go and choose to do something about it if you would like, but it's identifying for you where those overhangs are. And it's giving you a quick and dirty thumbs up, thumbs kind of middle, or like bad thumbs down if you're going to have a problem. The next thing is it's going to analyze for warping, because warping is a big deal on some of your parts. We can see that I have a positive thumbs up for warping, and my feedback here is saying that I'm not going to have much warping because I have a nice solid base for my part. If, however, I had a different part that had a very thin section on the bottom that's really attached to the build plate, I might get a, medium thumb or a thumbs down warning me that I'm going to have problems there. The same is also true for bed adhesion. Actually, I think I might have misspoke a little bit. The warping also has a lot to do with how thin the walls are and how straight they are, and whether there are supports for that wall, not just on like the against the bed of the machine, but within the part itself. I'll show you this in another example in a moment. And then the bed adhesion is more about what's actually attached to the bed. But the warping can also have to do with the bed adhesion, because if it doesn't adhere to the bed, then it's going to warp. So they're tied to each other in a lot of respects. Part size is going to be telling you if your part is too big for your build volume. That's why it asked for that build volume before. And then lastly, we also tell you the environmental impact of your part. And this one is a little bit more subjective in a lot of ways, but it's going to tell you a little bit more about the environmental impact of your part. And you can also click here to learn a whole lot more about that. I love this tool, this FFF or Additive Assistant. So I'm going to show you one other example of it. So let's go to my other Fusion 360 instance. And here I have, this is actually a really interesting connection. And this is for my shop vac. It actually connects my shop vac to my thickness planer. And it goes from a square duct to a circular duct. The square duct is on the thickness planer side of things, and then the circular duct is on my shop vac side of things. And I also have the ability to clamp this so that it's a nice tight fit and it's like nice and sealed. When I 3D print this particular part, I 3D print it where this surface on the bottom, this blue surface, is against the bed, and so it's sitting like this. And so let's go and run the Additive Assistant, but I could already see that this is actually upside down relative to the build volume. So I'll do the same trick like I was showing you before. And so I'll just go and rotate this 180 degrees. That's looking exactly like I like it. And then we're going to go and run that Additive Assistant again. I'm going to run this on this body in PLA, and I'm going to go and hit the inspect button. It's going to calculate for another, this one's about 30 seconds or so. And again, we'll look at those results and be able to see a whole lot of useful information from it. So give that just a moment while that calculates. And while that happens, I'm also going to do a quick little check on my questions from the chat window. So let's do a little check here. And I don't see anything super needing my attention right now. So that's looking really good. Let's get back to Fusion 360, I suppose. This is almost done. And then once that's done, we'll go and analyze it. Sorry, this is live, which means you do have to wait. While we're doing that, let's go and take a look at our PowerPoint, I suppose. So far we talked about the parameters, the Z height, and how you can minimize it to speed up your process, avoiding fillets when possible and acceptable. That's a very important caveat. Test your feature instead of your entire part, accessibility analysis, and now we're on the FFF consulting. We still have 4 more things left, and time check, we have about 20-ish minutes. So I think we're pretty good on time. So let's see if we are lucky and we have results. Yes, we do. All right, so in this particular case, overhang is giving me a thumbs up. The feedback here is pretty expected. I have some overhangs underneath here and underneath there that I should have expected. I have pretty good expectations in terms of warping, but the bed adhesion for a part like this is very bad. And it'll tell you a little bit more about that, but really I just don't have a lot of material against the bed. Now, depending on the settings you want to choose, you might want to use something called raft, and a raft will make like a big square area that connects directly to the bed of the machine, and then will connect to the part. You have some more cleanup to do after, again, unless you're using SR30, but that's what you're seeing. Let's zoom in here. That's what you're seeing. Again, the SR30 is the white stuff, but then the bottom, the black, is the raft. So the raft, even if this part, like the actual part, didn't have as big of a surface, the raft would be printing that entire surface so that I always get really good adhesion. But this FFF assistant is really kind of pointing out what those problems could be so that you can accommodate them. All right, so overall, I think that this additive assistant is super useful. So the next one is generative design. And generative design is a pretty awesome thing if you've never used it before. It is an AI-powered tool by Autodesk that helps you design and optimize structural components. So think of yourself, you're designing a bracket and you want to make it as lightweight as possible. In the past, we might have used tools called shape optimization or shape topology optimization. With generative design, it works a little differently. It's actually starting from the ground up, so to speak. So instead of starting with a final result and figuring out how you can lightweight it, it's actually starting with the more basic of like, what do you really need to design? Like, what are the critical areas of your part? And then it'll figure out how to connect all of those dots or areas together to yield you a final bracket. And you can use that to lightweight an existing part, but it's even more powerful when you're starting from scratch. So let me show you an example of that. We're going to go into my Fusion 360 again, and I'm going to show you an example that's pretty famous. You've probably seen this before. It's called the GE bracket, and GE for General Electric. And this particular bracket, the goal is to lightweight it, but just so you know, the loads on this bracket are substantial. This thing actually holds up a jet engine, like a jet engine on a commercial plane that you've probably flown in the past or flown on in the past. And when you're trying to lightweight a bracket like this, a lot of people will end up doing things like they'll shell out the part from the backside, and then maybe they'll add a rib or 2 ribs. They might run a finite element analysis to see if it's going to be strong enough. And then eventually they'll go and 3D print the part. And as they're doing this, as they're designing the part, they're constantly trying to design things that are going to be manufacturable in 3D printing or CNC machining or whatever other process they're actually using. But they're the ones who have to be aware of the manufacturing constraints and requirements. With generative design, you can put a lot of that work on the computer, on the artificial intelligence within the computer, so to speak. So how does that work? Well, we're going to look at the generative design area here. I'm going to switch this over. Oh, you know what? Before I show you how to do it, let me show you an end result that I think you will like. So let's switch over and take a look at a final result. This is an optimized part, significantly lighter than the original. But most importantly, this is optimized not just for the loads, it's also optimized for the manufacturing. In this particular case, for 3D printing in the Y direction. So this bottom here is flat. It doesn't look exactly flat. It actually is flat. And it's going to sit against the bed of the 3D printer, just like the one behind me. And everything else is actually going to be printable
with as little support as possible. And the idea behind it is that it does all of this for you. And if you're going to 3D print it, this can speed up your design process because it designs what's already 3D printable. So how does this work? Well, we're going to go into the generative design area here. I'm going to show you exactly how you start off in this. Let's go and that. All right. So these green areas are what we call preserves. They are the critical areas for this to function. If you remember from the design side of things that I had 4 bolt holes and I had an area over here. You know what? Let me show you this more clearly. There we go. So I have 4 bolt holes, 1, 2, 3, and 4. And then I have this area here that's going to support a pin. And those are the critical areas for this to function. How you connect them ends up being the shape of the part. But the function is really based on the bolt holes and the pin area. So if you hide the original design and you look at just the preserves, this is the simplest way to look at how you're going to design your part. Once you create these preserves and what we like to call obstacles, like what do you want to stay away from? And I won't go into too much detail on how I created this and stuff like that. You can watch other videos on YouTube, some of which that I've made that'll teach you how to do that. But the end resulting point here is that you specify what are the critical areas and then you let generative design do its thing. So let's go and take a look at some results here. It can create anywhere from one result, if that's all you want, to hundreds of results. And you can filter those results by weight, by material, by manufacturing process. And while I like to let it kind of like run unencumbered by just 3D printing, I tend to love the 3D printing results and I use them for a variety of different things. And so let's go and take a look at manufacturing method here. And I can hide everything besides additive. And what this is showing me is that these are all 3D printable results. And I can actually compare each of these or take a look at them individually. So it's really my choice of like, what do I actually want to take a look at? This one here is meant to be 3D printed in the Y direction, very similar to the one I showed you earlier, but the shape is actually very different. Again, though, you'll notice a very flat bottom, and all of the angles that you'll see here are within the requirements that I've set. And for a part like this, I've already set it to 45 degrees, but you can set this to whatever you would like. And the way that you do that is once you create the geometry that you'd like, and you set up your constraints and your loads, you're going to go into the manufacturing methods, and you're going to see quite a few different options here. The one that I want to focus on is the additive constraint. I'll put this a little bit closer to the middle so you could see it more easily. And you can choose the orientation that you're going to want the part in. If you choose Y plus or Y minus, you'll see the Y is actually my up, as I mentioned earlier. But you can choose whatever angle you'd like, or rather whichever axis you would like. We don't let you pick kind of a more random angle, like you can't just set this based on an axis, but you could also rotate your part and then use one of these global axes. That would be fine too. I also have set my overhang angle, and I also set my minimum wall thickness. And so this is very similar to like the parameter that I set at the beginning of this live stream, where I know that I have a minimum wall thickness and everything I do is going to be thicker than that. You're actually specifying that here. And then when it goes and generates all of those different options for you, it'll make sure that it meets the overhang angle requirement and the minimum thickness requirement relative to the orientation that you specify. And it does all of this automatically. And it does multiple different variations for you based on the materials that you've picked and the different options that you've picked. So again, if I look at just the additive results, I can start to compare different results with each other and start to see, which of these might make the most sense for my particular application. I'll go and pick 4 of these here right now. And then we can actually look at all 4 at the same time and start to really compare them to each other. Each of them are going to have their own pros and cons, right? And I can see a very different result between these two actually have a lot of similarities with each other. And then the top left and the bottom right actually have a lot of similarities with each other. but they're all actually very different. And all of them are already ready for additive manufacturing because I use generative design to do that. I do want to make sure I'm clear on this. If it hasn't already come up in the chat window, it probably will. The generative design feature set is available to commercial customers and does require cloud credits, which is, they do have monetary value. You purchase cloud credits and then you use those cloud credits to run generative design. You can do that a la carte, so per study. You can also get what we call the Generative Design Unlimited extension, which would allow you to run as many of these generative design studies as you could possibly imagine. If you're running this on a regular basis, and I highly encourage you to consider that because of how awesome this is, I would recommend the extension itself, as you will save a lot of money in the long run. But again, the key here is that by using generative design, you can actually design parts that are ready for 3D printing automatically. And you don't actually have to do much of the work yourself. Right? So I think that's really helpful. Back to our list here. The next one is another one of my favorites. It's the Zometry app for Fusion 360. So let's actually show you the app, and while it's calculating, I'll explain what it's actually doing. Let's go back to my screen and my video here. We'll go back to Fusion 360, and we're going to go and look at an example, and this example is going to be glasses. Actually, the model that you see on the screen, I hope you all recognize. I'm actually wearing them right now. So it's the same pair of glasses. I designed these in Fusion 360. There's a video on YouTube about how I did that. And then I 3D printed it. And you know, the printer behind me, the MakerBot Method X Carbon, is an absolutely phenomenal printer. But it's not going to be perfect for absolutely every application that's out there. There are plenty of situations where I might need a different printer, either temporarily or regular access to it. And if I'm not ready to actually go and purchase another printer, the Zometry app is a great way to expand my capabilities. So I'm going to go to Tools, and I've already installed the Zometry app, and I've already logged in with my username and password. And so what I do at this point is I select a component that I want to 3D print. For example, this frame in the very front here. And once I do, I'm going to end up analyzing this, which what it's really doing in the background is it's uploading to the Zometry website. And once it's there, it's going to use their AI and machine learning algorithm to give you a price to 3D print this part. Now, on first glance, you're probably thinking to yourself, why do I actually need to do that if I already have my own 3D printer? Well, I'll tell you, and this is where I think it becomes really important. All right, so first of all, let me actually select this so that we can get that running. And oh, something's a little funny on how I selected this. I'm going to have to clear that and fix this. Hold on just a second. Wasn't expecting that, but that's okay. We're going to create a component from this body. And then you do have to select components instead of bodies. So that's really what I'm doing here is I'm making it into a component. And then now I can go and select that component, and we'll go and upload that. There we go. That's what I was hoping for. We'll upload that to the Zometry website. And what it's doing is it's analyzing the geometry so that I could do all the pricing. All right, so that was a tangent. Why do I care about this? Well, the 3D printer behind me is an FFF or FDM printer. I talked about that a bunch of times. And when you're printing really small parts that you want really high resolution, you might want to use a different technology. SLA or stereolithography apparatus for nerds out there. SLA is a great way to get that really high resolution print, but it tends to end up curing kind of for the rest of that part's life, and it ends up not being as strong in my experience as some other methods. My favorites include SLS or selective laser sintering or HP multi-jet fusion or HP MJF is what that would be called. Now, these particular frames are printed on the Hewlett-Packard multi-jet fusion printer. So I don't have access to one of those. What do I do? Well, I can use the Zometry app, and I can select the manufacturing process. In this particular case, HP multi-jet fusion. I can select the material that I want to print this in, which is going to be nylon 12 when this pop-up lets me pick it. I'll let it finish analyzing, and then I'll pick it. And then it'll automatically give me a price. And what's really cool about this is that I mean, I don't have an HP Multi-Jet Fusion printer. They're like $150,000. And I could go to websites like shapeways.com or fictive.com or protolabs or fast radius, and I could upload an STL file and have them price it for me. But the Zometry app lets me do that right from Fusion 360 itself. And of course, because this is a live stream, this is giving me some headache. So I'm going to reset this. I'll do it again. I do want to make sure you see this. So I'll do is I'll turn this off temporarily and I'll restart it. And then that should do the trick. It usually does. Go and rerun that. I have to log in again, unfortunately. That's okay. And I'll reanalyze this and I'll show you the price. I do think it's worth the wait. So let's go and see if I can remember my password on demand. I think that's right. There we are. We'll try that one more time. Give that a moment to calculate, and then I will, of course, get the pricing. All right, so let's talk about the benefits. And by the way, we have an entire set of videos all about the Zometry app. If you end up wanting to explore it, please watch them. I'm part of many of those videos. But what the real key here is that I get instant pricing for a variety of different manufacturing methods. So SLS, SLA, FDM printing, and a whole lot more. But also that means that as I'm designing something, I could get a gut check on that price. So I could get a price for, let's say right now, the HP Multi-Jet Fusion. And then I could say, you know what, maybe that's a little too high for me. I want to adjust something in my design. And then based on that, I could get a new quote, again, instantly from the app itself. And that means that I could see if I was able to reduce that price or if I accidentally actually increased it. And that to me is really valuable in the design part of things. So as I'm actually designing, I like getting that feedback. And they say that a lot of your price is really based on things that are decided up front. But the reality is that there's still a lot of wiggle room for adjustment. And I want to be able to see what that price is on the fly as I'm designing. And I think that this Zometry tool does exactly that. On top of that, it allows me to expand the capabilities that I have in my shop, in my office. So while I have this printer and I use this almost every day now, the reality is that if I want to print something on an HP Multi-Jet Fusion printer, I could do that easily through this app. If I want to print it on an SLS or an SLA, I could do the same. This is taking far longer than I would like, unfortunately, right now. So I'm going to temporarily go to the next item and then take that back just in time. Let's go and select. Oh my goodness, I am having, oh wow. Oh, there it is. Okay, good. So I'm going to choose HP Multi-Jet Fusion. I'm then going to go and pick my material, and I'm getting a little bit of a glitchiness, but I still was able to get it done. All right, so this part would be $30.63. If I want to change to a slightly different material, I can go and do that as well. And then again, just recalculate it. Pardon me that the menu is kind of disappearing almost instantly, but the idea here is exactly the same. You could just go and choose your manufacturing method, choose calculate, and it will give you that price automatically. I'm not going to keep going with this, especially with the menu just disappearing on me temporarily, but just know that actually it typically works perfectly. This is the first time I've seen that problem, but you should try it yourself. You will have a great experience. All right, so next one, and there are only two left, I believe, is mesh to B-rep and the add or subtract a B-rep body from or to a mesh body. The last one is a mouthful, but it'll make sense once you see it. So let's get back to Fusion 360 here for a second. And actually, I want to open up that other instance, and let's go and take a look at this part. This particular part is a mesh file, or an STL, or an OBJ, or a 3MF type file. This came from Thingiverse. Actually, I'll show you this particular file just to really prove out what we're talking about here. Moment. And let's see here, mesh files, this guy. So this is an isobaric subwoofer. And I believe the isobaric is referring to like the pyramid shapes that you're seeing inside the subwoofer itself. But like most things on Thingiverse, this is going to be downloaded as an STL file. So once you download it and you bring it into Fusion 360, the first thing people typically ask me is, how am I supposed to edit this? How am I supposed to change the wall thickness or change the diameter for this set of screws, or change the hole for this screw, or whatever it is. And people typically struggle with that kind of thing when they're designing parts for 3D printing. But I'll tell you that we've had an update to Fusion 360's Mesh workspace on July 6th of 2021, so just about a month ago. And the updates are astronomically awesome. They are going to allow you to be able to make edits to this part very easily. The first step to convert this into a solid in a way that's very editable is to generate what we call face groups. And face groups are really just a way to group individual faces together based on similarities. Now for this part, it actually takes about 2 minutes for it to calculate. And the last thing I want for you is for you to watch and wait for that to happen. So I've already done that. You can actually see at the very bottom here, generate face groups 1 as a feature is there. And when you generate face groups, it's going to colorize everything so you could see them by the groups. At the moment, I'm not seeing it. All I have to do is change my display settings to turn on the face group visibility. And in a moment, you're going to see a pastel grouping of colors. Very colorful. The purple section here is representing what is intended to be a flat face. Same thing here. This is intended to be a fillet. This is intended to be a flat top. And the same thing even with these pyramids themselves. So it did a great job on a file like this to be able to figure out those face groups. Once you've figured out those face groups and you're happy with them, and you can, of course, update how it creates the face groups, and you could do some manipulation as well. But you can also go to convert mesh, and there are two options here, the faceted option or the prismatic option. The faceted option will give you a solid, but each of the faces or polygons in the mesh are going to end up being a face in the final part. The prismatic option is the magical, wonderful, awesome way to do things. So I'm going to show you what that looks like. I'm going to select this body and hit OK. And in about 5, maybe 10 seconds, you're going to be able to see in front of you, boom, I now have a solid body. If I look here, I have a gray cylinder icon. This is a solid body. It's a dumb solid body in the sense that there's no parametric history, but it doesn't stop me from being able to make changes. If I want to get rid of a fillet, for example, I could go and select that fillet and hit delete, and then I could go and change the fillet size to something else, whatever I want. I mean, I'm messing with the wall thickness over there at the moment, but you get the idea that you can make that change. You can come in here and change the size of the hole very quickly and easily, bigger or smaller, whatever works best for you. You could even change the face and drag this up or taller, or make this smaller or make that taller. Really, anything that you really want to do is essentially doable here. And the idea again is that I took that mesh file and I was able to convert it into a solid in a way that makes this incredibly useful. This is something that I've never seen possible in any other software. If you know of another software that can do this, please put it in the chat. I would love to do some research on what that software is. But in Fusion 360, I could do this really quickly and easily. The prismatic option that I used, just as a heads up, is only available to commercial subscribers. So I know that the 3D printing community has a lot of hobbyists or personal users. We are so happy and thankful that you use Fusion 360 for your designing and your 3D printing and your editing, but just know that that particular feature is gated for commercial users only. Fusion 360 is only $495 per user per year as of today's date, whatever it is today, August 12th, 2021. So if you're a hobbyist and you really like this feature, I would at least consider purchasing Fusion to access it, but just know that right now it's commercial only. Last topic, and let's read that again because it was a mouthful. Add or subtract a B-rep body to or from a mesh body. All right, so what am I talking about there? Well, the conversion I showed you a moment ago is fantastic, but that conversion is really meant for geometric shapes. So it works great for STL files, OBJ files, and 3MF files that are generated from CAD applications. Like right before you go to 3D print something, you save as an STL. It is a computer-generated STL file, and that's going to be great for this conversion to prismatic option. If, however, you're talking about scan data, that doesn't work as well for that kind of. And in many cases, the scan data has so many polygons that that conversion is kind of unrealistic anyway. So let's take a look at this example. And actually, I'm going to turn off the face groups here because this mesh is actually beautiful in color. But here I have a 1991 Dodge Ram Club Cab. And I have this CAD model because I might at some point need to reverse engineer a scan. And in this particular case, what we're really talking about is a scan of the hood ornament. And here you could see the hood ornament, the Dodge Ram hood ornament, and it is very detailed. In fact, if I get rid of the vehicle and we just look at the hood ornament itself, you could see all of that detail here, but you could really see it when you start looking at the properties. So if I go into this and I look at the properties here, you're going to see that under the mesh properties, I have 595,000 trees. That's a lot. If you are trying to convert this into a solid so that you can convert it, you might be able to do that. Actually, there's nothing technically stopping you from doing that. The 50,000 polygon limit that Fusion 360 used to have is no more. So if you would like to convert this into a solid using the faceted option, by all means, go ahead. But your hardware, meaning your computer, is going to be the limiting factor. If you don't have a super awesome computer, you are going to find that your performance is going to suffer greatly. So what I recommend in those situations is to leave the mesh as a mesh. Don't try to convert it. And when I say that, I still mean that you can add features to it or remove features from it. And so what I'm seeing here at the bottom of this particular hood ornament is a locating feature in the center and then two fastening features alongside it. So that's the screws that are, or bolts rather, that are going to hold this in place. And this was actually all done in Fusion 360. If I go back in time on my timeline here at the bottom, I'll show you what this actually looks like before I made those changes. It looks like a mesh that's just flat on the bottom. And so what I did was I created a plane on the bottom of this particular mesh, and then I created a sketch, which I'll show you here. And that sketch, let's go and bring that in there. That's what I wanted. That sketch is showing me the position of those holes and the exact size of those holes, and they're centered relative to each other and like symmetrical, and they look absolutely great. So once I'm happy with this, then I can start turning this into solid bodies. And let's be clear, on the left here, I have the mesh of the ram hood ornament. I'm gonna go and make an extrude for that center area, and that's body 1 at the moment here. Then I went and chamfered the edge of that particular guy. I extruded the sides, that's body 2 and body 3. Then I went and added my threads to it. They're a little hard to see unless I hide that mesh. There we are. And then once I've done that, I can actually convert those solid bodies into meshes. We call that tessellation. And under mesh here, I can actually tessellate those bodies. I've actually already done it, so I'll just go through my timeline. And what you're seeing now is the tessellated version of each of those threaded areas. So now I have body 1, body 2, and body 3, and those are actually mesh bodies, not solid bodies anymore. And then what I could do is I could use my mesh tools, such as combine, to combine everything together. So if I jump to the very end of my timeline here, you'll see that this ends up being merged into a single mesh body. And at this point, it is probably similar, but slightly different numbers. Now it's 595,962 polygons. So the point here is simply that I'm able to take a pretty darn complicated mesh like this, and instead of converting it into a solid for my design process, I could actually leave it as a mesh, and I can incorporate solid modeling and mesh modeling together in a way that I think is really useful. So let's summarize for a second what we were able to cover so far. We covered all 10 of my tips and tricks for designing for 3D printing in particular. Right, we talked about parameters, minimizing Z height, avoiding fillets when possible and acceptable, testing your feature instead of testing your part. I talked about accessibility analysis and draft analysis, as well as some of the limitations there as well. I talked about the FFF consultant or additive assistant. I also talked about using generative design as a means to design a 3D printable part without you having to do the design for manufacturing because it actually does it for you. I talked about the Zometry app for costing and also for additional 3D printing technologies that you might not have in your home or in your office. I talked about converting your meshes into BREP models so that you could then make changes to it using direct editing or a variety of other techniques as well. And lastly, I talked about using solid modeling and how you can add or subtract those BREP solids from mesh body. So we covered a lot today. And I have to say, I think that this topic is really useful because at the end of the day, we're all trying to make incredible things, right? That's really what Autodesk is all about, trying to make anything, right? As we like to call it. And with Fusion 360, you have all the tools at your fingertips to be able to design things. But what I've found is that it's a combination of having the right tools and then also learning how to use them. So today we covered my 10 tips and tricks for designing for additive manufacturing. I hope that you've enjoyed it. If there are some tips and tricks out there that I have not covered that you think I should know about, or I should at the very least be able to tell other people about, please put that in the chat window or in the comment section of this YouTube video. Please share it with others. Please give us feedback. We're happy to accept feedback, especially on future topics. I want to thank Brad Tallis for his time today on the keyboard and for your time watching today's video. So thank you very, very much for joining us. Again, I'm Jason Lichtman. I want to thank you for your time, and I hope that with Fusion 360, you end up making anything. Have a great day today. Thank you again. Bye now.